let us review some probability distributions commonly used in actuarial studies. In this video, I'll talk about discrete distributions. So you would have already known or encountered the Poisson distribution, the binomial distribution, the geometric, which we're going to review, and then also a few things about the negative binomial, which is perhaps new to you. As a first general comment, why are we spending some time on distributions? Well, as probabilists or statisticians or actuaries, our job or part of our job is to try to explain the random phenomena that surrounds us. And different phenomena have different characteristics, which might be well modeled or no by certain types of distributions. So in our toolkit, we want to have many distributions that have different characteristics that we can then use in different contexts. So let's begin. And we may start with the Poisson distribution. And pardon my French pronunciation of the word Poisson. So first, the notation, and this is a common notation when we deal with random variables, is this little wavy symbol, tilde. So x, and we can read this as follows. So x follows the Poisson distribution with parameter lambda. Now here, make sure you understand what a parameter means. So this is a parameter, meaning that it's a number which can take any values in a certain range. And because we don't know specifically what the value is, we just call it by a variable, by a variable name. And here we often use Greek letters to denote the names of those parameters. But lambda is just a name, right? I could have used theta, I could have used whatever. And here probably it's good to mention that lambda, in the case of the Poisson, is a positive. So it is a positive number. And to characterize my Poisson distribution, I can of course have what we've seen in the course, the probability mass function, which often is denoted little p of big X subscript and little x. Again, x is just an argument. And as you know, it's then a function that gives me the probability that the random variable, which has Poisson as distribution, takes a specific value little x. And this probability is given in the case of the Poisson by this expression. And this expression is a function of the parameter lambda. And again, lambda, depending on the context, can assume different values. It so happens that for the Poisson distribution, the expectation or expected value of the random variable is simply the parameter lambda, and the variance is simply the parameter lambda as well. So here you have so this is perhaps the most simple, maybe not the most, but a simple distribution because it only has one parameter and the interpretation is simple. The bigger the lambda, the bigger the expectation, and at the same time, the bigger the variance. Of course, you have that if you sum all the px, all values of x, and in this case, all the values are the non-negative integers. X equals 0, 1, 2, 3, etc. Then, of course, you get 1. Now, the Poisson is, let's say, the most common model for counts. If you're counting something, how many events happen, you can use a Poisson because it takes values in 0. So in case there's 0 events, 1, 2, 3, etc. Here it says that it's often used to model the occurrence of rare events. So rare events, how many of them happened? You might use a Poisson. A Poisson will not necessarily be a good fit, but sometimes it is. It says that you can use the Poisson to count the number of people who died, provided the parameter lambda is small, but this is maybe a side note. Okay, it's not that important. I would maybe add that, and we will revisit this idea a bit later in the course, but the Poisson is well suited in the following context. If there's a certain time period, can be whatever length, okay, from 0 to t, but t can be whatever length, 1 hour or 1 day or 1 year. But in this time period, there's going to be some events that are going to happen. Event 1, event 2, but the occurrence of the events is random. You don't know ahead of time when they're going to happen. But if those events happen absolutely independently of each other, then it's going to be the case that the number of events happening in this time period is going to be well modeled by a Poisson. So again, the key part is the independence here. If events don't affect each other's probabilities, they just happen, randomly, but also independently of each other, and you happen to count how many of them happen in any time frame, then this count is well modeled by a Poisson random variable. And we will revisit this idea later in the course in the last module, general insurance, and you will also see it more formally in other courses. Some simple numerical example. Let's say that the number of insurance claims on a particular yearly insurance policy has a Poisson distribution with a certain parameter here. So they give you the numerical value of lambda. They say lambda is specifically 1 in 100. So you see that this is an instance of rare events because the expected number of events is 1 out of 100. So it's the most likely event is that you have 0 claims. Maybe you're going to get 1, but this has a small probability, and then getting 2 is also a even smaller probability because on average you get just 1 out of 100. Then the probability that there's 0 events, well, let's not spend too much time on this. You just plug the formula. So you plug little x being 0 in the formula above. Then that's it. Then you obtain the numerical value, which is 99%. Of course, it's a very high probability because again, this is very low probability of events happening. So then the most likely case is that you get 0. You get 0 numbers. The probability to get exactly 2, same kind of thing. You plug 2 in this formula, and then you get an extremely small number, right? The probability to get 2 is not 0, but it's very small. The probability that you get at least 1, when you use again the trick that to get at least 1, you need to get, well, it's 1 minus a complement, and the complement of 1 or more is exactly 0. And then again, so you can use 1 minus the number we had here. So you get this probability, which is slightly less than 1%. Next, we have the binomial distribution. Now, the binomial distribution as a interpretation in terms of number of successes, but successes that you define success however you like in a given context, out of n independent trials. So there's a certain experiment that you repeat many times, well, n times in total. And for each time, you can have either have a success or a failure. So another way to say this is that an experience is repeated many times, and a certain event can happen for each trial or not happen. And then each individual trial has a probability little p of success. And then the binomial random variable is one that counts how many successes you had out of all the possible trials. So this is just an example, but the binomial could count the number of lives in a group of n independent lives, which all have the same probability of dying. So the binomial could count how many of them stayed alive. And then again, of course, here you could define staying alive as a success, and then p would be the probability of staying alive. Then you count how many stayed alive. But you could also alternatively define a success as dying, and then of course then the probability of dying would be the complement. of the probability of survival. Now, the hypothesis of independence is crucial for the binomial distribution. So each of those trials need to be independent, and by independent we mean that the occurrence of one does not affect the probability of occurrence of any of the others. If that's the case, as we've seen in the course, so the probability of a intersection of events, so the probability to get event, let's say A1 and A2 and A3, etc., under independence, this is probability of A1 times probability of A2, etc. Then in terms of the probability mass function, again, our little p of x, well, if we define our binomial to have the following, again, those are parameters, n and p, you call them parameters. Well, and with the restriction that n is an integer, well, positive integer, and p is a probability, so p is between 0 and 1. Then the probability to have exactly x successes out of your n trials is given by this expression. For x, careful here that all the possible values of x are 0, 1, 2, but we should add up to n. So the maximum value x can take is of course n. If you have n trials in total, you might have 0, 1, 2, or up to n successes. And it's given by this expression, which is what? Well, it's you choose x in n because out of all your trials, so let's say I label my trials, the first trial, second trial, third trial, etc., and I have n of them. Well, there's many configuration of which trial yields what results, right? Because let's say I want a trial with, let's say I want to find the probability to have 2 successes. Well, this can happen in many ways because I could have 2 successes the first 2 trials and then only failures. So that's one possibility. But of course, I could have a success at first, then a failure, then a success, and then only failures, and etc. I could start with 2 failures, then 2 success. So there's many possibilities. But in general, how many configurations there are? Well, you need to choose out of all your trials, you choose which ones have a success. And if there's x of them, or if you find a probability to have x success, then you choose x success out of the n trials. But each of these configurations with exactly x success has probability p to the power x, because you have x successes, times 1 minus p to the power n minus x, because in that case you then have n minus x failures. And each of individual configuration has this probability. So then you need to sum this probability for how many numbers of times you have a specific combination with that exact number of successes, x. And of course, in total, you have this number combination of x and n possibilities. For the expectation, I don't make the calculations of to compute the expectation of x, but it's equal to np. So, and this probably makes intuitive sense. You multiply the number of trials times the probability of a success for an individual trial. I imagine that you have 100 people, each have a probability of 5% to, let's say, make an insurance claim in a given time period. Well, on average, I expect 5 of them to make a claim. Of course, there's randomness. I might not get 5, but 5 is the average value. And then you have an expression for the variance, np times 1 minus p. Again, I don't prove this. Then we have the geometric distribution, which also has an interpretation in terms of events or independent trials. In a series of independent trials, And again, each of the trial can yield a success or a failure, each independent, each with probability of success little p. A geometric random variable represents the number of trials needed until you get one first success. So in this case, schematically, you could again picture some trials. This is the first trial, second trial, etc. And here, the geometric in those repeated trials, the geometric just counts how many trials are necessary to get the first success. So if I first get a failure, then I get a failure, then I get a success, then this means that my geometric would be equal to 3 because you needed 3 trials. But if you obtain a success at the first trial, then your geometric would just be 1. So then again, you can find the probability mass function, and it's not too hard. The probability to get exactly x trials, well, you need to get first x minus 1 failures. Here, the first 2 in this case are failures, and then you get your success. And this has probability exactly this expression, 1 minus p to the power x minus 1 times p. And then you know that x here takes values 1 is the minimum because you need at least 1 trial to have 1 success. 2, 3, and there's no set endpoint because in principle, in theory, you can take an infinite number of trials. Of course, this has a very, very low probability as the number grows, but still, in principle, any number of trials might be necessary to get the first success. Again, here we have some sort of numerical example. Passing or gaining exemption from actuarial examinations is notoriously difficult. Assume that the probability of passing or gaining an exemption for a particular exam is 0.6, so 60%. Calculate the probability that it will take at least 2 attempts to pass the exam. So again, similar calculations as before. Probability that I need 2 or more. So it's 1 minus the probability that it takes me exactly 1. Again, using the trick that the probability of an event is 1 minus the probability of the complement event. And then, well, you plug the formula over there. Maybe I should have mentioned those expression. The expectation of x is 1 over p, and the variance of x is this thing, 1 minus p divided by p squared. And the expected number of attempts required to pass is simply 1 over p. So in this case, 1 over 0.6, something like 1.66666. Here there's a note. It says perhaps slightly annoying, but different textbook define the geometric in a different way. So it's possible that you encounter somewhere that the geometric would be defined as the number of failures until the first success occurs. But you see that if the geometric is defined in this way, the value x equals 0 is possible. It's a sort of the same thing, but it's just every possibility is shifted by 1, because if you count the failures, well, it's possible to get a success at the very first trial, so then you have 0 failures. So just don't. This is just a note that you might encounter this, so don't be confused if you see a geometric with a different definition. Now for the for the negative binomial, it is in fact, if you will, a generalization of the geometric. In what sense? Well, let's just read the interpretation. In a series of independent trials, and each again with the probability of success little p, the negative binomial, which has 2 parameters, so careful here that unlike the geometric, we have 2 parameters. R and E. So it represents the number of trials needed until R successes occur. And here R, we should say that, so R is an integer, so R can be equal to, or I should say R take values in a set of positive integers. And P is the same as before, it's a probability. So you see that it's a generalization of the geometric, because the geometric is the negative binomial, but with specifically the parameter R equal to 1. You count how many trials are needed to get the first success. That's for the geometric. But for the binomial, you count how many trials are needed to get R success, where R can be 1, 2, 3, 4, 5, etc. And see that here, careful that what are the possible values that X can take? Well, the first one is R, because this would be the case that, in a sense, you're lucky. You get out of R trials, you get exactly R success. So you get your first trial, you get a success. The second trial, you get a success, and you get exactly R of them in a row. And in that case, well, how many trials did you need to get R success? Well, exactly R. But you see that X cannot take values smaller than R, because of course you need at least R trials to get R successes. This expression is the topic of a tutorial question, so I'm not going to explain it. So I think you can figure out why this expression holds, but because it's the topic of a tutorial question, discussion question in the tutorial booklet, I'll leave it for that occasion. Here you have a comment: a sum of R independent geometric random variables as a negative binomial distribution. Well, I think this, I'm pretty sure this is the topic of a tutorial question, but just to mention mathematically how we might write this. So if xi is a geometric with parameter p, or I equals 1 or 2 up to R, then the sum of xi, all the i's, and there's R of them. This is also a random variable, so careful that when you sum random variables, the result is also a random variable, because you have different random quantities. You sum all of them together, you still get a random quantity. And this random quantity as a distribution. So remember, we use this little tilde symbol to mean follows what distribution? Well, a negative binomial. Because you can prove this mathematically, but in words, think about it. I'm counting for the first X counts how many trials I need for the first success. Then the second X counts how many trials are needed for another independently obtained number of number of trials until a success. So if I sum x1 plus x2, what do I get? I get the number of trials needed to get to success. But if I keep this process, I sum x1 plus x2 plus xr, what do I obtain? Well, I obtain exactly the number of successes, exactly the number of trials needed to obtain exactly R successes. And this is precisely the definition of a negative binomial. How many trials did I need to obtain precisely R successes? I'll stop here for the discrete distributions. In a separate video, we'll review some continuous distributions.